Welcome to this explainer. Look, today we're jumping straight into what is arguably the most critical, hyper-complex, and honestly the most fragile manufacturing process on Earth. We're talking about the global semiconductor supply chain. It's the hidden engine powering literally every piece of modern technology you use, from the robot vacuum cleaning your floors to the absolute most powerful AI data centers in the world. It's an industry projected to hit $1 trillion in revenue by 2026, which is massive, but as you'll see, it's also balanced on a seriously precarious knife's edge.
Okay, let's just wrap our heads around the sheer scale for a second. 1 trillion. That's the staggering number of semiconductor devices shipped every single year. So that's over 100 devices for every man, woman, and child on the planet. But here's the wild part. Despite that massive volume, these components are incredibly fragile. We're dealing with microscopic features smaller than a virus. That's about 50,000 times thinner than a human hair. To give you a sense of what that means on the factory floor, a single human skin cell dropping from a worker could completely destroy a chip during production. And because they are so insanely hard to make, they're treated like high-security assets. The highest-end chips being produced right now sell for upwards of $30,000 each. Think about that. They are so valuable and so essential to pretty much everything that they're reportedly transported in armored vehicles. We're talking about the highly lucrative heartbeat of the modern global economy here. Basically, if it plugs into a wall or takes a battery, it absolutely depends on this supply chain. So, let's move into part 1, the insatiable AI boom.
You know, recently, something massive shifted the entire foundation of this industry. We've essentially entered a totally new paradigm. For decades, the semiconductor ecosystem ran on this predictable, cyclical timeline. It used to be that we'd wait for a company like Intel to drop a new processor, right? Consumers would upgrade their PCs, demand would spike, and then it would just kind of cool off. But that was the old era. Today, thanks to the sudden explosion of artificial intelligence, we're in a completely new era of sustained, relentless growth. The demand to build out massive AI data centers and supercomputers is just insatiable. We aren't waiting around for consumer upgrade cycles anymore. We are actively building the fundamental infrastructure for a totally new technological age.
To really put that trajectory into perspective, let's look at the numbers. In 2025, specialized AI chips, the ones designed to crunch massive droves of data and actually create software, made up about a quarter of all chip sales. But by 2029, that number is projected to cross the 50% threshold. AI is definitely no longer just some niche segment of the market. It's practically swallowing the semiconductor industry whole.
Which brings us to part 2, the micro-bottleneck, and a little something called extreme ultraviolet lithography. To truly understand how we actually build these incredibly complex AI chips, we've got to zoom all the way down to the microscopic level. And that brings us to just one Dutch company, ASML. Now, ASML doesn't actually make the chips themselves. They make the machines that make the chips, and they are literally the only company in the world capable of doing this at the highest level. To make chips even smaller and more powerful, ASML had to invent a way to harness extreme ultraviolet light, or EUV. This is a type of light that doesn't even naturally occur on the Earth's surface. The machines they built to generate this unnatural light are the size of a double-decker bus, they weigh as much as a blue whale, and they cost a staggering $400 million each. So, how does this actually work? Well, first, the machine generates that crazy EUV light. Next, it directs that light through a hyper-complex series of mirrors and lenses. And finally, it uses a special blueprint to shrink and transfer patterns directly onto a silicon wafer. This creates electrical pathways that are completely invisible to the human eye. And just to give you a sense of the extreme mechanics going on inside this $400 million box, the internal stages that move these patterns accelerate at 20 Gs. That's 4 times the acceleration of the world's most advanced fighter jets. And it's moving back and forth hundreds of thousands of times in just seconds. It is engineering that borders on actual magic.
Moving right along to part 3, Titans of the supply chain. Imagine for a second that you are an industry procurement manager. Your job is to source everything needed to build the modern world. You'd very quickly realize that absolutely no single company can do it all. You have to rely on this hyper-specialized division of labor. Take AMD, for example. They're the architects. They design the leading edge of AI processors, but they don't actually physically build them. Then you have TSMC, Taiwan Semiconductor Manufacturing Company. They are the ultimate bottleneck. They take those designs from AMD and physically manufacture them in these massive gigafabs. And then you've got Texas Instruments, or TI.
While AMD and TSMC are busy chasing those bleeding-edge AI chips, TI focuses on the essential analog chips. These are the foundational nuts and bolts that manage power and sensors. Because, let's face it, you can't build a trillion-dollar data center with millions of those basic analog chips. And for companies like Texas Instruments, the whole game is about volume economics. It's about making those basic chips as cheaply as possible and maximizing the yield. Right now, TI is making a massive $60 billion bet on transitioning from 200mm silicon wafers to 300mm wafers. Now, why do that? Because that seemingly small jump actually increases the surface area by 2.3 times. When you're dealing with tiny pepper flake-sized chips, that equates to hundreds of thousands of extra chips per single wafer. It is a total masterclass in using advanced manufacturing to dominate the foundational tech market. All right, on to part 4, geopolitical choke points. When we zoom back out to the global stage, we start to realize that this hyper-specialized collaboration is actually a highly precarious house of cards. Just trace the global journey of a modern chip. The heavy lifting in the actual chip design happens mostly in the US. Then, the raw silicon wafers often come over from Japan or Taiwan. That $400 million machinery we talked about to print the chips, that comes from the Netherlands. And finally, the actual manufacturing magic happens in fabrication facilities heavily concentrated in Taiwan. In fact, over 90% of the world's most advanced chips are manufactured by TSMC in a single geographic cluster in Taiwan. The entire modern world is completely dependent on this exact sequence holding together perfectly. Which really highlights the terrifying stakes represented by this number right here, $10 trillion. That is the estimated cost to the global economy if this supply chain collapses. And look, there are very real threats to it. Geographically speaking, Taiwan is prone to severe earthquakes. Geopolitically, TSMC is sitting right in the center of a decades-long standoff. China claims Taiwan as its territory, while Taiwan maintains its independence. Regardless of where you might stand politically on that issue, the objective reality for the supply chain is pretty stark. Any major disruption, whether it's a natural disaster or a military conflict, would instantly freeze the global production of basically everything. Smartphones, medical devices, military defense systems, you name it. So what's the solution? That brings us to part 5, the great global reshoring. Because of these massive existential risks, global superpowers have recently kind of woken up. They've realized they just cannot rely on this centralized house of cards. And that realization has triggered a frantic, completely unprecedented race to reshore chip manufacturing. Take a look at this. Back in 1990, the United States manufactured nearly 40% of the world's semiconductor chips. But by 2024, that number had plummeted to just about 10%. Labor costs and regulatory burdens just made it way cheaper to outsource to Asia. But given the new geopolitical realities we just talked about, plus the AI boom, the US and other global powers are now absolutely desperate to send that percentage climbing back up to ensure their own national security and economic stability. To try and fix this massive imbalance, governments are resorting to some incredibly large, unprecedented subsidies. In the US, you have the $52 billion CHIPS Act. That money is directly funding efforts like TSMC's $165 billion Silicon Desert project in Arizona, where they're trying to build highly automated fabs completely from scratch out in the desert. Meanwhile, over in China, because of US sanctions restricting their access to Western tech, they are pushing hard for self-reliance. The Chinese government has launched its own chip funds exceeding $50 billion to support tech giants like Huawei. They're actively building secretive domestic fabrication facilities to bypass those Western blockades. Basically, everyone is just throwing billions at the wall trying to secure their own piece of the supply chain. All of this leaves us with one final, incredibly important question to ponder. We've seen that the current semiconductor supply chain is honestly a miracle of hyper-specialized global collaboration. It took decades of fine-tuning to perfectly calibrate, but now, driven by the AI boom and some very deep geopolitical fears, governments are trying to aggressively rewire this $10 trillion choke point using brute force subsidies. The big question is, can money alone instantly recreate the world's most complicated manufacturing ecosystem, or are we destined to face a major global disruption before this new, reshored supply chain is fully operational? It is genuinely the most high-stakes infrastructure race of our lifetimes, and how it plays out will absolutely define the technological future of humanity. Thanks so much for joining me for this explainer, and keep your eyes on the silicon.